This is dissipated or lost or dissipated. This is the friction term.
Friction?
Yeah, this is the friction. Air resistance too. We'll do a lot of examples of these. But again, this potential energy is nothing new. It's just a work. But it's a work that doesn't have to be done by an integral. It can just be done by this new function called the potential energy. Okay, so that's a pretty straightforward derivation. Let's do an example of that. I'll start with some simple ones first. Are there any questions on that? I'll put it up here.
So you're saying, how would you describe potential energy in terms of an integral?
It's still an integral of the force over a distance, but you don't have to do the integral. Because it's path independent, all that matters is the beginning and end. No matter how you got there.
If that above equation given represents any conversion of mechanical energy, how do we generalize that for other forms of energy? Let's say the most basic ones.
That's these. These are all the other types of energies. This is everything. These are the mechanical energies.
Including heat.
Heat is friction. This is friction, this is heat, this is sound, everything is in these terms. But then this is mechanical energy. Yeah, that's a very general formula. That describes everything. There's nothing I'm missing in this formula. This is the formula I use when I do high level physics. So let me start with an equation. This is problem number 23 from the book, chapter 7. And the problem says you have this block and a ramp, and there's this force pushing, pulling it at some weird angle, 53 degrees away from the downward direction. So this angle here is 53 degrees. And it says the mass is 3 kilograms. It says that it moves a height up of 0.15 meters. So from here to where it moves is 0.15 meters. And this is the force that's being applied to it. And the question is asking you, what is the total amount of work being done on this what's the total amount of work being done on this block to move it up there? Okay, so we're going to start with this formula one more time. And it tells you it starts at rest. I think it tells you it starts at rest and it ends at rest. So you kind of move it up and just keep it there. Starting with that formula. And it doesn't tell you there's any friction, so I'm going to assume there's none. Okay, so there's no friction. And there's no kinetic energy change because it starts at rest and ends at rest. And so this term is also 0. So we've reduced this to something very simple. Just WU equals the work applied. And the work applied is whatever this guy is. This force is causing the work to be done on it, to move it up and changes potential energy. Right? And it's asking you what is this, what's the work that thing does to move it up that way. So on the left-hand side of the equation, you just have to put all the different types of potential energies that are converted in this problem. There's only one gravitational, there's no springs. So I'm going to write UF minus UI equals the work applied. And whenever you do these potential energies for gravity, you have to set your 0 point. That's up to you, because all that matters is changing. So just set it somewhere convenient. Usually you set it at one of the starting or ending points, because then one of them will be 0. So I'll set the 0 here. So I'll call that my 0 point, which means that the initial potential energy is 0, because it's mgh, that's 0. And the final is, now for gravity potential is mgh, something you need to know. And so I can put that in here and I'll get mgh equals the work applied. So this is very simple. The work applied is whatever the change in gravitational potential energy is. This is kind of a trivial problem, but it shows you the system that I use.
Would it be an angle in there also?
No, this is a good question. So the angle doesn't matter here at all. So what's very nice about the fact that it's a conservative force. It doesn't matter how I got the block from here to here. All that matters is I got it up 0.15 meters. I could have gone like this. Whatever. Get it there. I could have brought it up and then brought it back down, but as long as my final and initial distance is 0.15 meters, the change in potential energy is the same. This is a conservative force. It doesn't matter how you got there, path independent. So the total answer is just m, which is 3 kilograms times g times 0.15 meters.
So does the magnitude of the force and displacement are a triangle? Because the force.
Okay, if there are right angles, then yeah, you're forced, you're total, you wouldn't, it would take forever to get there. That's right. Yeah, and this problem, it says it eventually got there, so if you did get there, it would be there. All right, let me do another problem. So this problem actually, if you look at it, I'm gonna put this as a puzzler problem online. In fact, I was looking at this problem last night, and I was trying to do it using this formula, using f.dx, and I realized that was very non-trivial. It was extremely difficult, actually. Not really, really difficult. It took me a good 45 minutes to figure out like what it did. And the reason is they give you this weird angle, which is not the angle that's used actually in this dot product. So I'm gonna put this as a challenge problem. I'll put it up in a few days. It's not. So that's what's really tricky about this is you got to do a lot of work to find out what this angle is. Anyway, I'll put that up. But the point is that you don't need to know the angle, and it's a lot easier to just use work instead of having to use it. Yeah.
So is that a W applied is a gravitational force to do the work?
Work against gravity.
That's what you're doing against gravity. It's when you're pushing it up. You got to do it. Right. Everybody? Oh yeah, sorry. There's like a light.
So, if we're dealing with non-conservative forces, does that angle matter? Like, suppose there was friction.
If it asked you what the force was, it would. If it asked me, if it asked me like, here, this is a non-conservative force. This whatever is being applied. In theory, it might be non-conservative. So if it asks me what is this F, you do need to know the angle, and you need to know this way. But it just asks you for the work. So I'm just taking this whole thing and asking for that. In theory, you would need to know that. For friction, it always acts opposite to how you're moving. So for friction, the angle is 180. That's where that negative sign comes from. Okay, so let me ask you guys an algebra question, kind of as a conceptual question.
Set it up? No. I wonder if these count. If it's just glass ones. Because these aren't required. I think they're required. But I feel like I don't know if these count.
All right, so here's the situation up here. I'll put the wave baseline in a second. I think it's frequency double A. The situation is that you have some block on the surface here, and it's like a rough surface or friction. And the question is, I'm going to push one of the blocks a distance d right there and stop. And the second block, I'm going to push a distance 2d and then push it back a distance d. So they end up in the same place. All right, the question is, which one is going to require more work? A, B, or C is equal amounts of work? Which one requires more work? So all I'm only saying this, is that you're going to apply, there's a friction on the surface, so you're going to push it here and then stop it, or you're going to push it all the way over here and then bring it back. That's all I'm going to say. It's not going up or down.
So there is friction, right?
There's friction, yeah. Okay, so the question is, which one's going to require more energy to do? A, B, or C is, they're equal. Think about how friction acts. Looks like most people got their answer pretty quick, so I'm going to go this up for a couple seconds. All right. The result of this, most people said B, which is that the second one takes more. That's correct. Let's do the integral for this. So this, in this case, this is not a conservative force. Friction is not conservative. So the path doesn't matter. But let's do this out. I'll show you that the path matters. So for the first guy, the work is going to equal f.dx. Second guy, same thing, but I got to do two different paths. So in the first case, if I'm pushing this way, which direction is friction pointing? It's pointing that way. So the friction points this way, and the displacement goes that way. What's the angle between those two vectors? 180. 180, so the cosine, the dot product is negative 1. So here I'm going to have negative f times the distance I went. It's constant, I can bring it outside the integral, but it's negative because of cosine of 180. Okay? Now the second guy, I'm going to do the same thing. It's going to be, so I'm going to say for the first leg, and then for the second leg. Now the first one, the same thing, except it's going to go twice the distance. So it's going to be minus 2fd. Now when I push it back, I'm pushing it back this way. Which direction is friction pointing? That way, but I'm pushing this way. So again, the displacement is 180 degrees apart. So I'm still going to have a negative. So again, it's minus, and I'm pushing it back a distance of d. So this is minus 3f. Okay, so this guy took away this much work from the system. This guy took away this much. It's three times as much. So for friction, it matters how you got there. Whereas for a conservative force, if I threw it up versus just taking it up here without having it come up and back down, the amount of work would be the same. Because with conservative forces, you get your energy back. It doesn't go away. So most of got that. So let me move on. Let me just say one quick thing about power, actually. Power is, unfortunately, I forgot to put problems in the homework about power, but it will be in your test, so you do need to know this concept. Is it okay? So power is the derivative of work with respect to time. And so power, it doesn't just matter how you got there, it also matters how long it took you to get there. Let me do an example. Say number 46 in the book. 46 in chapter 7. This says you have an elevator. It's a loaded cabin elevator. This elevator. And the whole thing has a mass of 3 times 10 to the 3rd kilograms, so 3,000 kilograms. And it moves up 210 meters at a constant speed in 23 seconds. So it goes up 210 meters. 23 seconds, takes 23 seconds to get there at a constant speed. The question says, what average rate does a force from the cable do work on the cab? Let me read that again. At what average rate does the force from the cable do work on the cab? Average rate does a force do work. So it's a rate, so you know you're going to have it divided by a time there. That question is just, it's couched in words that means what is the power? So the average rate of the force is the power. Okay, so I got to find dw dt here. Yeah.
Sorry, one thing is this constant speed, motor power will be 0 because the force is 0. And constant speed means 0 acceleration, right?
Yeah, but it does take some energy to bring it up to that speed and then you slow it down, and that's what the power comes from. So in this case, you're going to do work because you're moving it from here to here, eventually. And that work is just going to be mgh. This is a very simple, just a change of potential energy. And the power is just going to be that divided by the time. So power is dw dt, which is mgh divided by the delta t. And it's average power, so it doesn't really matter kind of what happened in between, just the average, the total time divided by the total distance. That's why they say average power. Okay? And you plug the numbers, you get like 700 watts or something. Anyway, 3 times 10 to the 3rd times 9.8 times 210 divided by 23 seconds. And it's measured in watts, so the unit of power is watts. When you get your energy bill, when you guys start paying energy bills, they're not that much in San Diego, like $20 a month. Nobody uses energy out here. It's just like it's perfect weather all the time. Yeah, pretty Texas. This is where I'm from. So anyway, when you get your energy bill, it doesn't say watts. What does it say? Kilowatt hours. So the energy is in kilowatt hours, which is the same thing as a joule, because you're going to multiply the watts times the unit of time, which gets you back to an energy. So the energy that you get in your bill is, it asks you how many watts you use and how much time. Multiply those together, you get a total amount of energy. So it's not just how dissipated your lights are, like how many you're using at a time. It matters for how long you have them on, which makes sense. And that's just a unit, different question. But I just want you guys to think about this. So I'm going to have two different situations. Alright, so I'm going to have to do two different situations. Imagine a guy walking up a hill, and he wants to go up straight, but then he doesn't want to go up straight, he wants to take his time, so he does this direction, which takes about twice as much time. Now in these two situations, how are work and power compared? Alright, so in this case, the first one, he's going up a distance of, let's say, 30 meters or something. And the second case, he's also going up a distance of 30 meters, but he takes a more circuitous route to get there. So it'll take him a little longer to get there. So how do the power and the work in these situations compare? Can somebody explain that to me? Yeah.
Talking about is like that FV cosine theta one?
Maybe just more conceptually. I don't need to use a formula here. Like, which one's more? In these cases, which one has more work, which one has more power? Or are they equal in either case?
I'd say they have the same work, maybe the right one has more power.
Okay, you said the same work, but one of them, I think you said the right one has more power. So you want to explain a little bit? Sorry? No, this guy's taking a little longer time. Yeah, the guy he's going around taking a little longer time. Yeah,
Since the time is longer for the second one, the time will be greater, so the overall power will be less.
yeah, but the work
Stays.
work is the same because it's a conservative force. So all that matters is how high you went up. But the time takes more for this guy. So so when you divide by a bigger number, you're going to have a smaller power. That's why it's easier to walk up a hill going in switchbacks as it is to going straight up. Not because you're expending more calories per se. I mean, the thing about the way you do your body does work is it's not really conservative. So sometimes when you do faster, you actually end up burning more. But anyway, that's more of a minor issue. The other issue is that it takes easier to go up this way because your power is less, and you're taking a long time to get. But the work you do is pretty much the same. All right. Okay, so let's go to some problems that are a little trickier. These are kind of elementary problems, not too much work. Let me do number 49. Well, let's do number 2 on the homework. 2, 3, and 4. Alright, the first question is number 2 on the homework. Now this is the type of problem, if you use a formula, it's actually very straightforward. If you're not sure how to start it, I'll start off with the formula. So what it says is a ball of mass, 500 grams, is being thrown upward at a speed of 45 meters per second. And the question is asking you, how high does it rise? But you have to assume there's also a frictional force of 3 newtons when acting. And they're saying the frictional force is 3 newtons constantly. The question is, how high does it go? So what is the height that it rises to? If you throw up a ball, and there's a friction force acting of 3 newtons. Normally frictional forces depend on velocity, but I'm just going to assume that in this case it doesn't, to make it easier. And the question is, what is the height that it goes up? And it tells you it starts off at 45 meters per second. So the initial velocity is 45 meters per second. I'm going to start off with the same formula I did last time. Delta T plus delta U equals the work applied minus the work dissipated. The work applied here will be any sort of pushing or pulling. In this case, there's none, so I'm going to cross that one out. You do have some kinetic energies because it starts off the non-zero velocity. You also have some potential energies because it's going against the force of gravity. So accounting for both of those, I need to put that in the formula here. So I'll write TF minus TI, that's a change in the kinetics, plus UF minus UI, which is the change in potential, equals the work done by friction. Now for friction, I've already put the negative sign in there because we know there's going to be a 180 degree between how it's moving and where the friction is, so that accounts for the negative sign. So I'm just going to put the magnitude of the friction here times the displacement. This is going to be force times the displacement, force of friction times displacement. And the force of friction here is 3, I'm just going to call it FF. And we don't know how far it goes, but we know this is constant, so I can bring it outside the integral. So I get minus FF times whatever height it rose to. Okay? And I can do that because I can bring this outside the integral. Are there any questions on that part yet? Yeah, okay. So right here, I'm just writing the amount of work dissipated as the integral. This is the work definition, right? The negative comes because their vectors are opposite, so there's a cosine of 180 there, which gives you a negative sign. And then this is constant, so I brought it outside the integral. And then I integrated dx into the integral dx.
I have a question. What's the point of having the integral? So, like in this example, could we not just go straight to the its force times distance thing? Like, what's the point of having the integral?
The point is, if it's not constant, you can't do that. Let's say the force depended on the height, and it was 3x. You have to integrate that function, which would give you 3x squared over 2. It wouldn't just be whatever the force is times the height. It's a totally different function. So normally, in general, you have to integrate it if it's a non-constant function. Most of the examples you do in this class will be constant, so it's easier to do it.
If they gave you like a varying force problem, they give you the function to integrate.
Yeah, I mean, if they don't give it to you, then it's impossible to solve.
Yeah.
So that'll be given to you as a function.
Okay.
Yeah, maybe I'll think of a problem where that does it arise. Okay, so that's the work dissipated. Now I need to plug in the numbers here. So which one of these are 0? Any of these?
U initial and T final.
So the u's depend on where I put my 0 point. And again, you can put your 0 wherever you want. It makes sense to put it at the ground, so call that 0. So the initial gravitational is 0. The initial kinetic is not 0 because you're throwing it up, but the final kinetic is 0 because it's coming to a stop. So this is 0. And now I can just write this as 1 half mv squared, and I can write this as mgh. So I get minus 1 half mv naught squared. And the final rises to is mg times x. We'll call x the height. And the question is, what is x? So if you just solve for x, you'll arrive at the formula for x. Yeah.
Why is T at 0?
Because it's asking you how high it goes. So it's going to go to the very top where it'll stop, in which case the velocity will be 0 there. The speed will be 0.
How come you didn't use h instead of x?
I could. Yeah, I don't know.
But it would have made it harder to
H is just a
solve.
variable. H, I think.
Alright.
It's just a variable. Okay, so if I solve this for x, you get x equals, I'll put this term over here and this term over there. So I'm just solving this algebraically, and when you work it out, you get x equals mv naught squared over 2 times mg plus f. So this is not a trivial thing. I mean, this is a little more complicated than the kind of stuff you've been seeing in class. But systematically, it's the same system. You all start with the same equation and just plug in what you know. Are there any questions on that part? That was number 2. So all these things are given to you. It's very important that you guys, Professor Parr wanted me to stress this, is you're using these equations and getting an algebraic form before you put in numbers. You'll notice in the quizzes, whenever I make a quiz, I have a lot of questions that have responses that look like this, but they'll have numbers on it. And the reason is because it's important. It's more important that you know how to manipulate these things algebraically than it is that you plug in a number correctly. So I would recommend the homework as good practice to get in the habit of doing this and plugging the numbers in at the end. The other benefit of that is that if you get something wrong, it's easier to see where you went wrong. It's much harder when you see a number and you don't know what it corresponds to.
And this is actually, I feel easier to check the numbers because you can then, if you eliminate the frictional force, therefore basically if you get a height that is higher than the height would be the frictional force and not there, then you know you're wrong.
Yeah, you can do that when you plug the numbers out. I would still think you should plug it in. Alright, so that's the height that you rise to. Number 3 says, with the same problem, number 3 says, how much work is done in the ball by the air resistance? So that's asking for this, and I didn't, it says find the magnitude of the work, so if you get a negative number, just move it positive for that. How much of work is done in the ball? Well, the amount of work done is going to be whatever this is. This is the change in the work right here, this whole side, delta T plus delta U, and we just found that there. So if you start with the same formula, so work applied minus the work of friction. Now you can find this by just plugging in what you have for x and finding out what this total change in the work is, total mechanical energy change. And once you have that, that's going to be how much work friction did on the ball to slow it down. But you do need to know x, because if you go back here, I can find the kinetic energy no problem, but I don't know how high it rose until I solve this.
Can't you just use the force of the air resistance and multiply the weight on that?
But you didn't know the height. You didn't know the height until you performed.
Oh yeah, but I'm just saying, you know, with one generates, if you go there calculating kinetic energy again, when it's this calculating one work done versus two, that's
It could save you time too. All right, are there any questions on this? So this, you would just find the total change in work, and that's going to be how much work the friction is. You have the x now, so you can plug it in. I don't want to go through that. Maybe you got something to do. Any questions on that? Okay, number 4 says, the same question. Now we want to find out what the velocity is when it gets back to the bottom. So you've thrown it up, and it's come back down. Now there was a question, I think, in a previous homework assignment where I asked you when you throw up a ball, it said like compare the velocities when you throw it up and then when it comes back down. And you found on that assignment the velocities were the same magnitude but opposite in sign. In this case it's not, because some energy is coming out of the system, it's going to friction. So it's going to be slower when it comes down. You've lost some of the energy in that ball. So the velocity won't be the same, but that's only because of friction. Now to find this, there's a couple ways to do it. You're going to start with the same formula, but the reason I'm saying it's a couple ways to do it is that you can use your initial point either as a top and then use the final as a bottom, or you can use your initial point as when you first threw it up and then use the final as the when it gets back to the bottom. It doesn't really matter how you do it, you're going to get the same answer. I'll do the second method where I use my initial when I first threw it up. So this is right when I throw it up, that's the initial part, and then I wait till it comes back down to my hand, that's the final part. And I want to see what the difference in kinetic energy and potential energy is were between the very beginning and the very end. Right, so when I first threw it up, let me write this down. So TF minus TI plus UF minus UI equals the work of friction. You found this in part 2. This is all from part 2 here. And then this, well, I know that my final is going to be 1/2 mv, let's say vf squared. The initial, I already know the initial velocity, so I can plug that in as well. And this is what I'm looking for here, the final velocity. Now also, your UF and UI, those are both 0 because you're starting and ending at the 0 point. So those equal 0. So you see that it's actually pretty straightforward. You have this number from part 2. You know this because you can plug in your 45 meters per second, and you can solve for VF. Okay. If you started from the top, you'd be able to get the same thing. Now, that's probably good practice if you have the time. Use the top as your starting point. In that case, you do have potential energy, but you have no kinetic energy. So you're going to have the same formula, but different terms are going to be 0. Are there any questions on that?
if you work from the top, then your potential energy, when your potential energy initial is not 0, the kinetic energy final is not 0. Essentially you'll get almost the same formula as the second problem, but just will be mg minus ff. Therefore, that's the only difference in the answer. And x will be known, will be unknown. Therefore, that's why it's not easy to transfer the top as the 0 formula. But then you just need to modify the top formula just a little bit.
Any other comments or questions?
Does this apply if you wanted to know the initial and final position, not resting, like while it's still in the air? Like you just
Oh, so his question is if you want to know like how long it would take to get like halfway up or something?
yeah, like it goes up in the center, not from the ground. It's still in motion. Whenever it still had kinetic energy, right, in the top.
Yeah.
So instead of that taking it from this top and bottom, we just take a section of the same would it still apply?
The formula would still apply, but you would need to know what the velocity was at that time, which would make it harder. The reason this is easier because if you start from the top, your velocity is 0, so that term drops out. In theory, you can start from the middle, but you have to find the velocity. Let's see. Okay, I want to do another problem that's... So, by the way, today I'm going to probably teach until like 9:20 at least. There's a lot of stuff I want to cover. If you want to leave before that, that's cool, but I'm going to probably teach until about that time. I want to do one problem from the book because I want to emphasize the importance of choosing what's called a system. This is number 49 in chapter 7. Chapter 7.
I'm too tired.
so this question says this. It says there's a fully loaded, slow-moving freight elevator, and it has a mass of 1,200 kilograms. And it's supposed to go upward 54 meters in 3 minutes. Okay, so its total height change is going to be 54 meters. And it says the elevator's counterweight. So the way these elevators are constructed is there's an elevator and it's attached over some pulley to some weight that allows it to go up easy. So let me just draw that in this picture. There's a counterweight, which it only has a mass of 950. Okay, so if you just let this thing like how it was with no other forces on it, the elevator would just drop, right? So there's going to be also, it says, the elevator's counterweight only has a mass of 950, so the elevator motor must help. And it asks you to find the average power of the motor. So let's find the work of the power instead. Sorry, the work of the motor. To find the power, is divide that by the time. So the first step is let's find how much work the motor has to do to bring it up 54 meters. All right, so you're going to have an extra motor here. I'm going to just draw it like this. So here's your motor. And it's going to be helping this counterweight, this other mass right here. This mass weighs 950, so it helps you bring up the elevator to some extent, but it's not strong enough by its weight alone. You have to have an extra help, which is what the motor does. That's going to pull it down. And the question is, how much work is that going to do? In other words, you've got to find the either you can find the work of the motor or find the force first and then multiply by the distance. So the reason I'm going to do this problem is not because it's really a tricky problem. There's an easy way to do it. But I want to show you the importance of choosing a system. And when I say choosing a system, it means what are you going to call your system that you're considering as the internal system? And once you know what that is, what are the external forces on that? So let me give you two methods to do this. Method one, let me say choose a system. This is something you already kind of do just naturally, but it's good to know kind of how you're doing this. So method one is, I'm going to choose, let me just draw this free body diagram. Okay, so here's the counterweight, here's the elevator, and there's this force of the motor pulling down. I'm going to choose this as my system. Now, if I choose that as my system, whenever I write down kinetic energies, I only need to consider the kinetic energies of that moving body. Whenever I write down potential energies, I only need to consider potential energies of that moving body. But everything else that's attached to it is going to count as an external force. So if I write this down, there's no friction, so I'm not going to write it down. Then this will be, I guess this will be 0, because it kind of goes from rest to rest. This will be non-zero because it's going against gravity. And this will also not be non-zero because there's a cable pulling it up. There's an applied force on that. And it's not a conservative force, so I have to do the integral and do a little bit of work with that. I need to find the tension also, because I don't know what that force is. And that involves doing the stuff we did in chapter 4, finding, using the free body diagram, etc. I'm going to start that one off. I don't know if I'm going to take the time to do it, but let me just show you kind of why this is a tricky method. Not a tricky method, but it's a longer method to do this. So if I did this, let me write down this formula here. I would have delta U equals the work applied. The work applied is the tension. It's just one dimension, so I'll just write tension dx. Okay. And the tension is constant because it's all forces, so it's just going to be constant acceleration. This is going to be t times the total distance you travel upward. That means I need to find the tension. If you want to find a force, you got to use free body diagrams. It's like we did in chapter 4 and 5.
So this case we have two equations of K unknown. We have the free body diagram.
Well, let's see. So the tension here, we got to go and look at a free body diagram. So let's see what I have. So I'll call this mass 1 for the elevator and mass 2 for the counterweight. So for mass 1, which is the elevator, I have its weight pulling down. I have the tension pulling up. Then for mass 2, I have its weight pulling down, I have the force of the motor pulling down, and I have the tension pulling up. And it's just in one dimension, so that makes it a little easier, not have to do x in the y direction. There's no components. Now if I write down the free body diagram for this guy, it's just going to give me T minus W1 equals M1A. This guy is going to give me T minus W2 minus F motor equals M2A. minus A. The reason I'm putting minus A here is that my coordinate axes are like this. If this guy goes up, this one has to go down. So they have to have opposite acceleration. Same magnitude, but opposite. Same magnitude because they're connected, but opposite because one goes up, the other goes down. Alright, now the goal here is I gotta find the tension. So in this equation, I have everything I need except I need the acceleration. So I'll solve this one for acceleration and plug it in, or do the vice versa. Let's do this one.
What supports the motor on the second map?
Sorry?
What is the motor force on the second map?
Well, just I drew it so that's connected to the second max. You can connect to the first one and do the same thing. So I'll solve this for A. This will give me A equals W2 minus F motor minus tension over M2. I just divided by negative M2. And I'll plug that in here. So we get 2T minus W1 equals mass 1 times all the accelerations. We did a lot of problems in chapter 4 that were, at least as complicated. This is not, it's not anything what you've done in class.
You still have two unknowns, F motor.
Sorry?
You still have two unknowns, F motor and T.
Right, but we're going to plug in T here, and we're going to express the F motor in terms of this stuff. So we still have two equations between us. So let's solve it for T, because again, the goal here is I want to find the potential energy change I have, but I need to use that to find, I need tension, and I can write the motor work in there. So I'm just going to write down what this is when I solve it, just to save time. You can verify this for yourself if you like later. So the tension is 2 times the weight of the first guy, plus M1 over M2 times force motor divided by 1 plus M1 over M2. It's not a simple formula. And I plug that in there. Let me go ahead and do that actually. So I'll plug that in here to this formula, which gives me delta U equals all this times D. And this guy also is mgd because it goes up. The total energy change of gravitation is just mg times the distance it went up. So that's that side. Now the goal here is what is the work of the motor, which is going to be F motor D. So I want to find that. Okay, I'm not going to go through the work, but here's what you end up with. Got that done.